And the most exciting aspect of being a scientist is discovering something new for the first time, learning something new every day, working in an environment driven by curiosity and creativity, making an impact, intellectual or otherwise, and options for so many exciting career opportunities. Okay? So, if you want to be a scientist, be open. Don't brand yourself physicist, chemist, etc. Because when you brand yourself, you kind of like lock yourself into a small little well. And you got to know your passion and understand your skills. Because if you understand them well, you can combine your skills and passion and create a career. A career in science and engineering can lead to anything. It's a matter of aligning your interests and your skills to what the society wants. Okay, in order for you to get it. As a matter of fact, last week, Intel surrendered to TSMC, and Intel finally decided they cannot do the 7-nanometer node, and they're going to outsource their work to TSMC. And this has been a major shock to the entire semiconductor community. And always keep asking the question, what impact can I make if I succeed? What do I do to make an impact? And you keep asking that question because that makes you think like a leader, not a follower. And then you can be a leader, because anybody, I believe, can be a leader. It's just that it's your mental attitude that makes you, think the right way.
And abroad. So welcome everybody to this second talk of Expert Talks by Raising a Mathematician Foundation. In this talk, we have a very eminent guest with us, Professor Venkatesan. Professor Venkatesan, if you can turn on your video. So we have here with us today somebody who is an accomplished and very senior person in the scientific community. So let me just give a short introduction of Professor Venkatesan. Professor Venkatesan completed his tenure as a director of Nano Institute of Technology, Nano Institute in the National University of Singapore, and where he was a professor of ECE. And he has a lot of achievements to his credits. He has been he was working at Bell Labs at Belcore in US for about 17 years before he became a full-time professor of University of Maryland, again for another 17 years. And he became the inventor of pulsed laser deposition, PLD technology. And he has written over 690 papers and has over 32 patents in the area of oxide thin films. He is also the founder and chairman of Neocera or Neocera, a company that specializes in the area of PLD, magnetic field imaging systems. He is a recipient of various awards. He has guided close to 10 of the researchers who are doing PhD and postdocs. And he is a fellow of the APS. He is a winner of Belcore Award of Excellence. He is a winner of George Pake Prize awarded by the APS 2012, and so on and so forth. So he has got a lot of credits, and we are very happy to have you with us, Professor Venkatesan. Over to you.
All right. So I was told that all of you are in essentially 10th to the 12th grade in school, and many of you are at a stage in your life wondering what you are going to become. And clearly, for many of you, the option is to become a scientist. And I'm sure there are a lot of peer pressure in terms of what you should or shouldn't become. And so in my talk, I'm going to give you some rationale as to why become a scientist. Okay, and I realize that this message is very important to give to high school students because they are at a very impressionable age, and that's a time when they don't know the whole lot about the world, and they're very reliant on other people's opinions, and sometimes, very often the opinions of even the people closest to you can be disastrous. So I'll give you an example of that. So my daughter went to school in a prestigious school in Singapore named Anglo-Chinese School Independent. This school in international baccalaureate was world number one. Okay, just broke every record, and it was just an amazing school in terms of its performance. So I went to the parent-teacher meeting, and the CEO of the school put up very proudly the performance of the school and how the student admission in various fields into colleges, for example, has improved every year. So in the field of medicine, he said, we went from 2009, 14% to 2010, 16%. Law, students admitted from 12% to 14% increase. And in business, it went from 15% to 17%. And he kind of like stopped at that point. I was wondering, what about science and engineering? So I'm not someone who keeps quiet. So I stood up and I said, what about science or engineering? And all of a sudden, there was like an absolute dead silence in the room, the whole hall. All the parents were looking at me like, where did this alien come from? Who is this guy? Doesn't he understand anything about our norms of our society? So I'm kind of like feeling really awkward. And then the CEO looks at me and he says, well, in our school, we really don't, our parents really don't care about science or engineering. They're most concerned about medicine, law, and business. Okay. So you see, essentially, a large section of the students who would have actually gone into science because of their own natural curiosity would have been completely turned away by their parents to go into, fields like medicine, law, business, where you're likely to make more money on the average. Okay, so money was the driving force, and security, job security, and these are the issues, and decisions were made. Okay, so it became very clear to me that I had to really do something to change the attitude in Singapore, particularly. And what happened is that I was invited to be a guest speaker for the national labs. They're called A-Star laboratories, and they normally take exactly students of your vintage between 10th grade to 12th grade, and they pick the best brains in the country, roughly about 200 of them, and they get to do research in these facilities. Okay, and the whole aim of that is to encourage some of them to go into science. Okay, so I was asked to give a talk on some scientific topic to inspire them in the final graduation day. So the topic of my talk was this: defy your parents, become a scientist. Okay, and all of the cartoons in this were prepared by my daughter Tara, so I've got to give her full credit for all of these. And so this was a rebellious talk where we had to fight against the parents so that the kids can become scientists if they really wanted to become scientists. The real sad part was at the end of the presentation, where all the 200 kids received awards, when I did a poll, and they said, how many of you are going to pursue science? And out of the 200 kids, only 10 kids put up their hand, which again, in my mind, was a real travesty, because, it's such a sad thing that so many of them could have gone into science and had a fantastic career. There are a lot of misconceptions about science, going into science. Popular misconceptions are: be prepared for life bordering on poverty, unending sequence of postdoc positions till a real job appears. And if you go into a faculty line, you toil away to get a tenure. By the time you get a tenure, you're already burnt out. And also, if you go into any scientific institutions, your bosses will steal your prize-winning ideas. And the highest level one can aspire for is to become a professor. And some people say, yuck, is that it? So this is how the world is thinking. What I want to do is I'll give you an example of, my case, for example, and show how, entrepreneurship is a pretty exciting option for people going into science. And so let me now, why is it moving? Okay. So the reality of a scientific, if you're in science, there are some really unique things about being a scientist. And I just want to bring these things out to you, okay? First is when you're in science and you're doing research and you're as a scientist, when you do research, you're actually working for yourself, actually. The research that you're doing is mainly for your own curiosity, your own interest, and as a result, it's highly driven by your own ego and your own, what I call, aspirations. And second point is, research is a universal language. For example, let's say you're doing something in quantum physics or whatever, then this knowledge that you is identical whether you go to Japan or whether you're in Argentina or you're in Chile or in Spain. Everybody speaks the same language of science, okay? And it's so remarkable because I would go to some with my family to, we go on some trips to various cities, and I will just, challenge them, and I'll say, look, I'm sure if I call this university here and I go to the physics department and tell them that I've come here, and they'll probably invite me to give a talk since I'm here in the next few days. And sure enough, someone there will recognize me and say, okay, give us a presentation here. In a sense, what it is that it's truly a universal language, and you can have relationship with people all over the world. And that is extraordinary for in any kind of a profession. You can't say the same thing for law. You can't say the same thing for other fields, basically. And there's no limit to how far you can aspire to. I mean, you can, if you're hardworking and you want to go very high in your career, you can. And it's, of course, it's a way of life. It's not like most scientists. They don't work like 9 to 5. They're always thinking of ideas all the time, and so it can be all-consuming sometimes. But the most interesting thing is you're learning all your life, and your brain is always working, and it keeps your brain young. Okay. And if you really want to make money, there's a lot of opportunities to make money if you're a scientist. It's just that you have to do things a little differently from what traditional scientists do. Okay. So in my talk today, I'm going to basically take a very fundamental physics concept, which is interference, and how I have taken this concept in a quantum mechanical sense and created a company based on this. Okay, so I'll give that as an example to show how, we are taking a subject in which we are continuing to publish papers, right? And at the same time, if we identify a proper application for this scientific idea, you can actually come up with a winning product that essentially generates money. Okay, so I'm going to talk about interference phenomena. In a classical interference effects are like this. For example, here's water waves in a pond. So you drop two pebbles, one here and one here, and the wave generated by them, they intersect at a point and they create what's called an interference pattern. Okay. So in an interference phenomena, it's very easy to illustrate it. For example, let us say you're running through a crowded street and there are other people running. Okay. If a person running next to you is running in the same direction and collides with you, you will actually move forward even faster. So on the other hand, if a person is not in phase with you, but is moving in the opposite direction and collides with you, you'll come to a stop, right? So this is a simple example of an interference phenomena. When two waves, the points in the wave intersect where they are in phase, that means they're moving in the same direction, it's called constructive interference. So the amplitude goes up, whereas if they are in opposite direction, they will destructively interfere, so the amplitude goes down. Okay, so this leads to all kinds of fascinating phenomena that we see in a daily life. For example, this is a soap film in a soap bubble, for example, right? And these are the colors that are generated because the soap film is very thin, and the light that bounces from the front and the back side of the film, they interfere with each other. And depending upon the thickness of the film, they constructively or destructively interfere at different colors. And so wherever there's a constructive interference, that color stands out. And so you can see this at this particular thickness, it looks very pinkish. Out here, this looks green, and so on. So you get this very beautiful interference colors in that thing. Similarly, these are actual shock waves generated from supersonic jets in the atmosphere. And they're also gravitational wave interference. Now, these are all classical interference, but quantum mechanically, you can also see, for example, a single photon itself can interfere with itself, as demonstrated here. And you can also have matter, so here you can see these molecular patterns where the molecular interferences take place. And you can see maxima and minima where the molecules are constructively and destructively interfering with each other. Now, what we do in our experiment is we take a superconducting film, which I show here. So we send superconducting current along this wire here, and this wire now branches into two branches, and then they rejoin again here, okay? So essentially this current is split into, essentially partly this way and partly this way, and the two current then come back and, combine here and effectively create an interference here, okay? Now what happens is when I apply a magnetic field to this loop, the electrons in the supercurrent here, or the electrons are actually called Cooper pairs. I don't want to get into the details of this stuff because that's not central to my talk. But essentially, to be technically correct, I should really call these electrons as Cooper pairs because they're paired electrons. That's why it manifests superconductivity. But these paired electron Cooper pairs essentially experience a different force on the left arm versus the right arm because of the magnetic field. So on one side, they get accelerated, on the other side, they get decelerated. So you can kind of sort of say that way. So what happens is when they recombine at the other end, the other end of the wire, the amount of phase difference between them, whether they're in phase or out of phase, depends upon the strength of the magnetic field. So essentially, you can essentially have constructive interference or a destructive interference on the other side, but that depends on the strength of the magnetic field. And by measuring this current output at the other end, we can actually measure what magnetic field is going through this loop of wire here. And this is essentially a magnetic sensor. And it's one of the most sensitive magnetic sensors that we know in the world today. And it's called a superconducting quantum interference device, or a SQUID. And this is so sensitive, it can measure the magnetic field of the brain. So in our brain, the neurons fire and they are essentially constantly in a dynamical state, and they're generating neuronal currents. And these neuronal currents generate essentially magnetic fields, and you can actually measure these magnetic fields by using a SQUID, okay? And there's a whole field of people, researchers working in this area, okay? And there is another very interesting magnetic sensor, and this is called a GMR, or Giant Magnetoresistive Sensor. And this sensor works on the principle that there are two magnetic plates, electrodes, and you send electrons from one electrode to the other electrode. And essentially what happens is the electrons are spins, and essentially when the electrons go from one electrode to the other electrode, which is all ferromagnetic electrodes, what happens is that if the electrons are aligned with the magnetic direction of the electrode, the ferromagnetic electrode, the electrons are allowed through. If not, they meet a resistance. So again, this is another way by which we can actually, by measuring the resistance of the electron across this barrier, we can actually measure a magnetic field. And interestingly, both these phenomena, this high temperature superconductor that we use to make the squid and the giant magnetoresistive sensor that we also use to make a magnetic sensor, both these phenomena were offered Nobel Prizes in the last 15 years or so. I mean, both these won Nobel Prizes. So we make sensors out of them, and then we build a machine where these sensors are scanning over a surface, and on the surface is placed a sample. And in this case, I proposed at that time, this was several years ago, I proposed that we work with a company like Intel, and all of you have heard of Intel. And so we worked with Intel to essentially demonstrate that we can actually locate flaws in circuits by measuring the magnetic field generated by the currents flowing in the circuits. And I'm going to show you how that actually works. Okay, so this is my company, Neocera. This company I founded, when I was in Bell Labs. I left Bell Labs to essentially form a company that would will productize the invention that I made at Bell Lab, and the product was called Pulse Laser Deposition System. And so Neocera was formed to, essentially market those equipment. So under the same company, we started making this scanning squid and scanning GMR microscope. So this is essentially a magnetic current imaging system. We call it Magma, and it is sold today to all the semiconductor companies. Now, why is this market and why is this an opportunity? Because when a company like Intel or Samsung or TSMC, they introduce a new chip, okay, from a process line, these chips are built on fundamental designs, electronic designs, and they're extremely good. But despite that, to produce the chip, they have to go through so many different processes, so many steps: metallization, dielectric layer, etching, lithography, all sorts of stuff. And so by the time the final chip production occurs, right, the yield, which is really the measure of what percentage of the chips are working, right, is never 100%. Very often the yield is like 20%, 30%. Then they have to take a defective chip and try to figure out what is wrong with it so that they can fix the right step in the process flow. So in order to find out what is wrong with the chip, they need a tool that will tell them where the defect is. And the common defects are short, open, a resistive open, or a leakage. So these are the four types of defects that are normally found in chips. And you need instruments to locate where exactly these defects are. So on a chip or a package, what they will do then is, once they located where it is, they will then they'll do surgery on the chip, cut open that small region and find out what really went wrong. And this is the kind of detective analysis that needs to be done. And then they will figure out, okay, what should I change in my process line so that the defect doesn't occur, okay? So this whole field is called failure analysis in semiconductor industry. And there's a big market for tools in the failure analysis industry. And this is essentially the market our tool is addressing, basically, okay? So, for example, I'm going to give you some examples of how this device really works. So let's say there's a wire carrying a current, okay? You all learned in your physics class that the wire generates a magnetic field. And the way you look at it is you use what's called a right-hand thumb rule, okay? So you grab the wire with your hand and your thumb goes in the direction of the current, okay? Then your fingers, which are curling around, give you the direction of the magnetic field. So the magnetic field is essentially circular around the wire, as I've shown here. And so you can see now, if I take my sensor, which is indicated as this green square above, which is your squid, for example, and I now start moving from left to right, what will I see? On the left-hand side, the magnetic field is actually going downwards. And then when it goes right above the wire, it becomes a 0. And then when I cross over to the right-hand side, you can see it becomes positive. It goes up. So this is now reflected in the form of a color map here. Red means down, white means nothing, and blue means upgoing field. So you can see the magnetic field pattern now is there's a red pattern, white thing in the middle, and a blue on top. Now, this is an actual package. It's a multi-chip module package from Intel. So it's got many layers in it of current flowing. And this is an example of a magnetic field generated by the current that is flown in this device, okay? Now, if I take what's called Biot-Savart's law, which is you learn in physics how to convert, let's say, a magnetic, a current into magnetic field, you use Biot-Savart's law. So we do an inversion of that, and you get this current pattern. So we're effectively using the magnetic field image to create the actual current pattern in the chip. What's beautiful about this is that we've not even opened the package. There's a plastic covering on top, everything, and the signal comes, all the magnetic signal come right through all the materials that are used in the semiconductor industry. So it's in that sense almost like X-rays, right? It really like comes all the way through. And one of the interesting things you notice is that the current here is very weak, and then it becomes very bright. It zigzags around like a meander line, and then it gets a little weaker and becomes very weak. And the reason for that is because the current is actually coming from different layers. So this is the bottommost layer, which is farthest from the sensor, jumps up to the layer which is closest to the sensor, then goes one level lower, and then even lower level. Therefore, the intensity goes. So essentially, we have depth information obtained in this data, basically. When we overlay the data that we have with the CAD drawing, that is shown here, the Intel engineers say, oh, the current shouldn't have gone here. It should have gone along the meander line here, but instead it broke off to the left. So there's a defect right there at that point. So we're able to locate a defect to very high spatial precision at that point, okay? So this is how the defect was developed. Now, when you work with companies like Intel, actually, they educate you on what they want, and they try to, so when they see a company like you're coming along and we're helping them solve their problems, they will tell us what to do and so on. So for example, this is a chip from Advanced Micro Devices, and there is essentially a leakage point here. So what I see here, which I shown red here, is actually, this is a whole, if I look at a chip and I look at it in terms of the current flowing in the chip, it's like a rivers and tributaries and streams flowing all over the place in a chip, actually. So, but where there is a leakage, you can see here, the very high intensity point here. And that shows up like a star in a night sky, basically. So this is where there's a bunch of transistors that are leaking. And so they're located, now they can go do essentially post-surgery and analysis of why that leakage occurred there. I'll give you another very interesting example where you combine more than one tool to locate a defect. Here is a package in which there is a short of some kind, okay? So you can see the currents are coming in here and the currents are leaving here, and there is some kind of a short because the currents are not appearing inside the chip. So there's something is shorted here, okay? So where could that be? So you now overlay the current image with, this is an X-ray image of the metal. Okay, the X-ray image gives you density information. It doesn't give you electrical information. And what it shows you that, okay, here's an electrode, here is an electrode, and our currents are going this way, and they're suddenly coming around and coming this way. So that means there's a short right at this point. And then when you zoom in with your X-ray image, you can see what has happened. There is a solder reflow. That means there's silver solder that is used in bonding this wire and this wire here. Some of the solder seem to have gotten here, and it has created a short here, right at this point. You can see. So this is the type of kind of analysis that is done. Sometimes one tool is used and sometimes multiple tools are used to detect the thing. Now, one of the big challenges that happened was that they wanted higher spatial resolution. Since our squid actually uses liquid nitrogen, we couldn't get the detector close enough we could only operate at a distance of 40 microns from the surface. So the best spatial resolution we could get was like 1 micron or so. But now with the GMR sensor, we can take the sensor right up to the surface because it's a room temperature device. So here, for example, is a current pattern here. The current is flowing down this meander line here, and you can see now the image here is the current image, exactly imaged by the GMR sensor, because I can get right up to the surface, and you can see that I'm able to separate two wires which are 300 nanometers apart, and you can see the spatial resolution of the current is close to 100 nanometers or so. So we have solved the problem of the resolution which Intel raised. We were able to solve it by using a different kind of a sensor. So the combination of these two sensors then gives us the ability to solve a variety of problems. Then the guys at Intel said, okay, hey, 60% of our problems is not shorts and leakage, but opens. And we can't look at opens. Now the problem that became the huge problem, because opens means I can't send a current in an open. So how do I generate a magnetic field? And this became a big issue. The way to measure opens is they use something called time domain reflectometry. So what they do is they send a very short pulse, electrical pulse, and that pulse, what it does is it'll travel down a metal line, and wherever there's an open, it'll be reflected and it'll come back to the original position. So if now I can measure the time TDR signal, which is a pulse that goes in, and I look at the reflected signal, by measuring the time involved between the incident and the reflected signal, I can figure out how far the open is located. Okay. But the problem with this is the speed of electrical signal in circuits is essentially, 10 to the 10 centimeter per second. I mean, like multiples of 10 to the 10 centimeter per second. And therefore, even in, say, 10 picosecond, the pulse travels too far. And therefore, you don't have spatial resolution. This technique, which is today used in the industry, can get defects down to maybe, a millimeter or fraction of a millimeter, but it can't do better than that. And it's a destructive technique and requires real expertise. So we put our head together and we came up with a new idea called standing domain reflectometry. And this idea is very simple. It is, if I take a DC current and pass it in a wire with open, the current will not propagate. But if I send an AC current or a high frequency current, the current will go down the line, it'll reflect off of the break and will come back. It'll set up what's called a standing wave. And essentially in a standing wave, the wave will have a minimum at the open point. And then you'll have like a sine wave after that. And these are like, because they're standing waves, they'll be like that. So for example, if I send a signal that is like, say, 200 megahertz in a wire, the actual wavelength of this is meters, basically. A 200 wavelength is 1 meter or so. So that length is huge compared to the device dimension, right? So what happens is your device is really small. This is the wavelength of your 200 megahertz wave that I'm sending down the wire. So what actually happens when a standing wave is set up at the open, what you actually see, if I look at the intensity of the wave here, the wave will be, very strong here, but as I come towards the open, you see, it's a sin x function, but as x becomes very small, you all know that sin x is like x, right? So it goes linear. So it just becomes a linear function. So if I take the intensity, if I can image my high frequency signal, and I just image its intensity and then extrapolate it to 0, it'll cut exactly where the open is, all right? So this is the whole idea behind standing domain reflectometry, which is invented by my company. And so here, for example, is a wire, okay? And we laser cut the wire here at this point. And look at the intensity. The squid is actually imaging the high frequency signal here. And you can see that that signal is essentially the intensity now. When I extrapolate it to zero, this is standing wave intensity. It just cuts at this point, and we know exactly where the open is, okay? And this is, for example, here is a meander line. The wire is going back and forth, and we laser cut an open right at this point here. And we put the current from both ends, from this end as well as both ends. And you can sort of see the intensity is dying down. You can see it's really dying down. And right at this point is where you can see this intensity coming down. And similarly, the intensity is coming down. And right at that point is the intersection point. So we can actually locate an open defect. This is like a remarkable achievement, you know, and the most remarkable thing is the competitive field, our competition can locate an open to an accuracy of about a fraction of a millimeter, whereas we can locate it down to 10 microns, basically. So it's really what I call a disruptive technology. Now, here, for example, is what is called a through silicon via integrated circuit chip from Fraunhofer Institute in Germany. And what really, this is a meander line of actually, so the current is coming from here, it is going across, and from here it goes inside the page, and it comes out on the other side. There's a similar electrode on the other side, and the current then comes up from here. So the current is actually going up and down and up and down. This is called a daisy chain, and the current is going up and down. And there are 1 million of them in this circuit. And we actually image the entire thing. We power it up, and we can image exactly how this daisy chain is working. And you can see these are the magnetic field images that we see here. And this can be converted into current image here. So you can see the current images are different colored. The different colors represent bottom current or middle current or top current. And essentially, you can see the whole lot of stuff. And this is becoming important because today, the whole semiconductor field is becoming three-dimensional. So the way you increase the circuit density was making the transistor smaller and smaller and smaller. But now we are reaching what is called, this entire process was called Moore's law, where, you know, the circuit density would basically, you know, double every year. And now what has happened is that Moore's law is kind of reaching its limit. In other words, we are now at the transistor size is approaching 7 nanometers. And essentially it's getting very, very expensive to shrink transistors now. In fact, the cost per transistor used to always go down when we went from, you know, one dimension to the next, you know, reduced dimension, but not anymore. Once we reach this, you know, 7 nanometer node, the cost per transistor is actually not going down, and it's remaining flat and may even increase if you go to lower dimension. So economically, it's becoming less of an incentive to try to go even smaller, okay? So it's much more what I would call the company's own, like what I would say, showing their mettle that they're trying to show that they're really good at it and they're trying to do this. As a matter of fact, last week, Intel surrendered to TSMC, and Intel finally decided they cannot do the 7 nanometer node, and they're going to outsource their work to TSMC. And this has been a major shock to the entire semiconductor community because the Intel could not complete their process. So that's another interesting story. So you see so you see how an interference phenomenon, a quantum interference effect, or a spin interference effect can be utilized for magnetic field sensing. And if you identify a market application for it, you can actually create a product that you can sell all over the world, basically. So right now, we sell this tool I'm the CEO of a company named yesterday Magma, and we just spun off this company this July, and our goal is to continue to sell this tool all over the world to not only semiconductor companies but also companies like Apple, Nvidia, Qualcomm, Broadcom, and all these companies that even though they don't make the chip, they design the chip and get it built by somebody else. Okay, so even Amazon, for example, is our customer. So it's very interesting. The whole world is heading in that direction. Okay, so I would like everybody to think in terms of one thing that I would like to leave. You incorporated. Me incorporated. Think that way. Me, I want to be, running something by myself. I want to create value, whatever it may be in society, but I want to do it. You want to be a leader. You want to think that way, right? In other words, the moment you say, I need a job, will I get a job in a company, right? You become suppliant. You become already, you've surrendered your soul, okay, at that point. But I would say, if I think like you incorporated, okay, I can make something happen. I can provide job for others, okay, with my ideas, okay. When you think that way, it's very empowering. And you'll see, you look at the world in a very different way. You look at friendship, you look at collaborations, you look at, your attitude changes dramatically at that point. Instead of competing with people, you'll collaborate with people, and you will try to bring people to your way of thinking, try to develop a vision, these sort of things. Okay, so this is really, to me, the real formula for success, basically. Okay. All right, thank you all so much. Okay,
thank you, Prof. See you later.